So if you're tuning in late right now, maybe you're, staring at the glow of your monitor, taking a break from debugging some massive monolithic application.
Oh, we've all been there.
Right. And you know exactly how satisfying it is to finally, map out a totally bloated system and realize, hey, I can actually make this run 10 times faster on a fraction of the hardware.
The dream of every software engineer, honestly.
Exactly. And that is exactly the journey we're taking today in this deep dive. Because what if I told you that for years, literally the sharpest minds in the tech industry were just burning billions of dollars in server time?
Just setting it on fire, basically.
Yeah, building these colossal AI brains that were, mathematically speaking, just starving to death.
I mean, it sounds like an exaggeration when you put it like that, but looking back at the architecture from just a few years ago, the inefficiency is staggering. They were brute forcing their way to intelligence.
And just completely ignoring the underlying, nutritional requirements of the models.
Exactly. They didn't understand the diet these things actually needed.
So to figure this out, we're looking at the stack of sources you sent over. Specifically, the original 2020 Kaplan scaling laws paper from OpenAI, the really disruptive 2022 DeepMind Chinchilla paper, and some recent engineering teardowns on what the industry is now calling the data wall.
Which is a huge problem right now.
Massive. So our mission today is to dissect how one specific mathematical revelation completely reversed the AI world's obsession with, massive parameter counts and handed state-of-the-art capabilities back to everyday developers.
Yeah, and to really appreciate the magnitude of that Chinchilla breakthrough, we have to look at the deeply entrenched dogma that it completely dismantled. We have to go back to 2020 and look at those Kaplan scaling laws.
The era of bigger is always better.
Right.
Because when OpenAI published the Kaplan paper, it really felt like they had discovered this fundamental law of physics for machine learning.
It did. It was treated like gospel. They established this very predictable mathematical relationship between the physical size of a model, its parameter count, and its overall intelligence.
Which was basically a green light for hardware maximalism. If you want a smarter model, the most compute-efficient way to get there is just to physically scale up the neural network.
And for a software engineer looking at those 2020 findings, it looked like a straight-up irrefutable engineering equation. I mean, the parameters, which are the variable weights and biases the network adjusts during training, those were seen as the absolute primary bottleneck to learning.
So Kaplan's math basically dictated that if your budget for computation increases, say you manage to acquire 1,000 more GPUs, you should spend the vast majority of those new floating point operations, or FLOPs, on just adding more parameters.
Rather than passing more data through the existing architecture. Exactly.
It feels a bit like adding an endless number of cylinders to a car engine.
Oh, well, that's a good way to put it.
You're building this ridiculous 500-cylinder monstrosity, assuming the sheer capacity of the engine is the only thing that matters for speed.
Right, right.
But you never stop to optimize the fuel injector, or check if you even have enough gas in the tank to keep all those cylinders firing. Were developers just blindly stacking parameters because hardware was scaling and just assuming the data would sort itself out?
I mean, the 500-cylinder engine is an apt analogy, but we need to understand why Kaplan's team came to that specific and flawed conclusion. Because they didn't just guess, They ran actual experiments.
Right, they were doing the science.
They trained a series of models of varying sizes and plotted the performance curves. But the problem was their methodology. They mostly trained and extrapolated from relatively small models up to about 1.5 billion parameters.
Which seems tiny now.
Tiny by today's standards, but more importantly, they didn't properly adjust their learning rate schedules for the larger data sets.
Okay, wait, let's break down that mechanism for a second, because the learning rate schedule, that dictates how large of a step the model takes when updating its weights during backpropagation, right? So if you don't adjust that schedule properly, when you feed the model significantly more data, what actually happens under the hood? What breaks?
Well, the model basically stops absorbing new information way too early.
Really?
Yeah. As it processes more data, the learning rate typically decays. It takes smaller and smaller steps to fine-tune the weights without, destabilizing what it has already learned.
Okay.
But Kaplan's team kept the learning rate schedule tied to the number of training steps in a way that just didn't scale optimally. So when they tried feeding larger data sets to their models, the learning rate dropped too quickly.
It was like they just stopped paying attention.
Exactly. The models essentially shut down their ability to learn before they had fully digested the extra data.
Oh, wow. So the researchers looked at the result and thought, Well, adding more data didn't improve performance much, but adding more parameters definitely did.
Yep. They mistook a poorly tuned optimization schedule for a fundamental law of compute scaling.
That is wild. And that single methodological blind spot launched an absolute parameter count arms race across all these massive tech conglomerates,
Everyone started building the biggest brain possible based on this totally flawed assumption that data scale was secondary to parameter scale.
which gave us the monolithic behemoths. I mean, we saw GPT-3 roll out with 175 billion parameters.
Mhm.
Then DeepMind's Gopher hits 280 billion. Google's PaLM eventually comes in with a staggering 540 billion parameters.
Just massive.
The engineering required to just shard these models across thousands of GPUs just to run a single training pass, it was astronomically complex.
Oh, the distributed systems engineering was brilliant, truly. But the fundamental resource allocation was completely skewed. That brute force parameter stacking eventually hit a wall.
And not because they couldn't physically string more server racks together.
No, no. It was because another team of researchers finally stress tested the math on a much wider scale. They actually looked at what these behemoths were eating.
Enter March 2022. The DeepMind team publishes the Chinchilla
The
paper.
bombshell.
Yeah. And the core disruptive finding that shocked the industry was that all of these billion parameter giants were massively undertrained. They were, going back to our analogy, running completely empty on fuel.
DeepMind mapped out what we call the compute optimal frontier. So instead of just tweaking one variable, they ran over 400 different training runs. They created isoflop curves.
Wait, isoflop curves, just to clarify for everyone listening.
Oh, sure. Imagine you have a strictly fixed budget of compute, say 10 to the 21st power floating point operations.
A very specific, very massive number.
Exactly. You can spend those operations multiplying a massive matrix a few times or a smaller matrix many times over a much larger data set. They systematically varied both model size and data volume across these fixed compute budgets to find the exact point where performance peaked.
And out of those isoflop curves emerges the new golden ratio. For every single parameter in your model, you need to feed it roughly 20 tokens of training data to maintain optimal compute efficiency.
The famous 20-to-1 ratio.
And for the engineers listening, we're talking about standard tokens here, right? Like the raw subword chunks of text the model ingests.
Yeah, exactly. And that 20-to-1 ratio was a devastating reality check for the existing ecosystem.
Let's apply that math retroactively to the poster child of the era, GPT-3.
Let's do it.
So it had 175 billion parameters. By the Chinchilla rule, you multiply that by 20, it should have been trained on roughly 3.5 trillion tokens of text.
But GPT-3 was trained on only about 300 billion tokens.
Wait, 300 billion, so it was operating at less than 1/10 of its optimal capacity.
Less than a tenth. The servers were spending weeks processing these massive matrix multiplications, doing forward and backward passes across 175 billion weights, but the model wasn't seeing nearly enough distinct examples to actually refine those weights into useful concepts.
The computational waste is just hard to overstate.
It's the definition of inefficiency. Allocating FLOPs to update a parameter that isn't receiving enough novel data to learn anything new.
But as an engineer, looking at that 20-to-1 ratio, my immediate reaction is, frankly, logistical dread.
Oh, absolutely.
I mean, if I'm building a 100 billion parameter model, you're telling me I need 2 trillion tokens of high-quality data. That sounds like a logistical nightmare. Was anyone even collecting data at that scale back then?
Gathering parameters just requires a massive checkbook to buy more NVIDIA GPUs. But gathering trillions of tokens of deduplicated, filtered, high-signal human text
That requires scraping the entire public internet.
and somehow filtering out the SEO spam, the bot traffic, and the terrible machine translations, that data pipeline nightmare is a major reason the industry was so eager to accept Kaplan's laws initially.
Oh, because scaling hardware is a clean, solvable infrastructure problem.
Precisely. Scaling high-quality data is an incredibly messy, unstructured data engineering problem. Nobody wanted to deal with it.
Which means publishing a paper with elegant isoflop curves wasn't going to be enough to turn the ship. DeepMind had to prove to an industry deeply financially invested in parameter scale that the 20-to-1 ratio actually worked in the wild.
They needed a physical demonstration, a true David versus Goliath showdown.
So they built their new model, Chinchilla, and specifically designed it to go head-to-head with their own previous monolithic monster, Gopher.
Right, so Gopher was the Kaplan-era giant, 280 billion parameters. Chinchilla was built with just 70 billion parameters.
Exactly 1/4 the size.
Exactly. But the crucial constraint, the variable that makes this a valid scientific benchmark, is the compute budget. They trained both models using the exact same number of FLOPs.
Okay, let's look at the mechanics of how that compute budget is spent during training. Because training a neural network is essentially a relentless cycle of matrix multiplications.
Yep, it's just math all the way down.
When you have a 280 billion parameter model like Gopher, every single forward pass to generate a prediction and every backward pass to calculate the gradients and update the weights requires a massive amount of memory and compute.
Because the matrices you are multiplying are physically enormous.
Precisely. But if you shrink the model down to 70 billion parameters, your matrices are much smaller.
Much smaller.
So each forward and backward pass becomes mathematically much cheaper.
And because each step is cheaper, you can perform 4 times as many steps within that same fixed FLOP budget. So while Gopher spent its budget supporting the sheer weight of its parameters, over 300 billion tokens, Chinchilla spent its identical budget passing 1.4 trillion tokens through its smaller, much faster network.
And the outcome completely dismantled the prevailing dogma. Chinchilla outperformed the 4 times larger Gopher on every single benchmark.
Every single one.
Reading comprehension, mathematics, common sense reasoning, coding tasks. It wasn't just a marginal victory. It was a clean sweep.
And the mechanism behind that victory redefines our understanding of network intelligence. It proves that efficiency isn't about the size of the neural network. It's about how thoroughly those parameters are forced to learn.
It's the difference between a sprawling, disorganized warehouse and a highly curated, perfectly indexed filing cabinet.
I like that.
I mean, Gopher had 280 billion parameters, but a huge chunk of those weights were essentially dead space or highly redundant. They just hadn't seen enough varied examples to crystallize into distinct, useful concepts.
Right, whereas Chinchilla's 70 billion parameters were forced to work incredibly hard, compressing a massive diversity of data into a much tighter architectural footprint. More data creates denser, more useful representations.
And this is where the theoretical math crashes into the practical reality of software engineering. Because proving a model 1/4 the size could achieve state-of-the-art results, that didn't just win academic debates.
No, it completely shattered the hardware barrier to entry. The implications for inference, the act of actually running the trained model to generate text, were seismic.
Yeah, because a 280 billion parameter model requires a highly specialized multi-GPU cluster just to load the weights into memory. It is entirely locked within the domain of enterprise data centers.
But a 70 billion parameter model, that crosses a critical threshold. It's still large, sure, but suddenly it enters the realm of what a determined organization, a university lab, or even a highly optimized local workstation can actually host.
Which naturally caught the attention of researchers over at Meta. They looked at the Chinchilla findings and realized they could push the logic even further to optimize for the end user.
The llama ripple effect.
Exactly. Meta takes the DeepMind data and flips the priority.
Yeah.
Chinchilla was about finding the compute optimal ratio for training. Meta decides to deliberately overtrain.
They effectively said, we are willing to spend an inefficient amount of compute during the training phase if it means we can shrink the parameter count even further for the inference phase.
Because inference is where the actual cost of running an application lies for developers.
Yeah.
So Meta releases the llama models. They drop the parameter counts drastically down to 65 billion, 13 billion, and even 7 billion parameters.
But they train them on massive data sets. They push 1.4 trillion tokens through that tiny 7 billion parameter model.
Wait, let's do the math on that.
Right.
By the Chinchilla standards, a 7 billion parameter model only needs about 140 billion tokens to be optimally trained,
Right.
pushing 1.4 trillion tokens through it. That's a 200-to-1 ratio.
It is. Mathematically, the later stages of that training run yield drastically diminishing returns per FLOP.
But the end result is a fiercely capable model that has been compressed down to a size that can run locally on a high-end consumer laptop.
Yeah.
I mean, as an engineer, watching this unfold was incredible.
Oh, for sure.
For years, AI architecture was heavily centralized, guarded by massive tech conglomerates with supercomputers. And the Chinchilla math was the catalyst. This is the moment the technology left the ivory towers and landed right on the laptops of regular software engineers. It's like moving from mainframe computing to the personal PC.
It really is. Democratizing the architecture shifted the entire industry's momentum. Suddenly, you have a global, decentralized community of software engineers downloading model weights, fine-tuning them on local data, building specialized applications, and aggressively optimizing the inference engines.
It kickstarted the massive open-source LLM revolution we see today. But empowering the entire world to train highly efficient models using the 20-to-1 token-to-parameter ratio, well, it created a brand new, incredibly urgent bottleneck for the whole industry.
Yeah, we solved the parameter bloat, but we drove ourselves right into a solid brick wall. The industry is currently colliding with the data wall.
The data wall. Let's map out the logic of this collision. We now know that to build smarter models, we have to scale both parameters and data simultaneously, maintaining at least that 20-to-1 Chinchilla ratio.
Right.
The problem is, if you scrape the entire public internet, you don't find an infinite well of usable training material.
No, you don't. The internet is unfathomably large, sure, but the signal-to-noise ratio is terrible. State-of-the-art models require high-entropy, complex data to learn reasoning. They need published books, peer-reviewed scientific papers, meticulously curated code repositories, well-moderated forums.
But when you filter out the SEO gibberish, the spam, the duplicates, and the low-quality machine translations,
Yeah.
you are literally left with a strictly finite pool of high-quality human knowledge.
Exactly, and looking at the engineering blogs from teams currently training the next generation of models, they are scraping the bottom of the barrel. Humanity simply hasn't written enough good text to satisfy the math required to train a multi-trillion parameter model optimally.
Which is wild to think about.
It is, and this specific limitation is aggressively driving current AI research into new frontiers, primarily synthetic data generation.
Right, so the proposed solution to the data wall is using existing, highly capable AI models to generate billions of tokens of high-quality text, mathematical proofs, code, and then feeding that simulated data into the next generation of untrained models.
Which, as an engineer, I'm sure you have thoughts on.
Oh, it immediately triggers alarms from a systems engineering perspective.
Hmm.
If we start training new AI models on data generated by older AI models, aren't we just building a digital echo chamber? Doesn't the quality of the signal eventually degrade into noise?
You are pointing directly at the phenomenon of model collapse. It's a severe mathematical degradation that happens when networks train recursively on synthetic data.
It's almost like aggressive JPEG compression, right?
Yes. Perfect analogy.
Every time you save the image, the algorithm approximates the data. You lose the subtle pixels, the sharp contrasting edges. Do it enough times, and you are just left with a blocky, smoothed-out distortion. What is the actual mechanism driving that in a language model?
It comes down to probability distributions. Human language has a massive, complex, long tail of nuance, rare vocabulary, and unique logic structures.
Right.
But an AI model, by its very nature, learns to predict the most probable next token. It tends to over-index on the center of the distribution, the most common average ways of phrasing things, and it underrepresents the rare edge cases.
So when the AI generates synthetic text to train the next model, that text is already stripped of the long tail.
Exactly.
The next model trains on this smoothed-out data, learns an even narrower distribution, and outputs even more generic text.
The tails of the distribution get chopped off with every generation. Without careful algorithmic curation, the model amplifies its own biases and hallucinations, loses its grip on complex reasoning, and eventually collapses into producing repetitive, nonsensical outputs. It forgets the richness of the human data it originally came from.
Wow. This really frames the data wall as something much more complex than just a storage or compute limitation.
It is a profound challenge of signal integrity and data integrity that your generation of engineers is going to have to solve. Overcoming it requires algorithmic breakthroughs. Researchers are currently exploring how to selectively filter synthetic data or combine it with targeted reinforcement learning so the model explores new logical pathways rather than just regurgitating the mean probability of its predecessor.
Looking back at the trajectory we've tracked today, it is a phenomenal study in optimization. I mean, we started in the Kaplan era, watching the industry burn through massive compute budgets to build bloated, inefficient monoliths based on a flawed extrapolation of learning rates.
And then DeepMind's Chinchilla paper fundamentally realigned the math.
They mapped the compute optimal frontier, proved that these networks were starving for data, and established that elegant 20-to-1 ratio.
Which directly enabled Meta to push the Llama models, optimizing heavily for inference and effectively handing the architecture over to the open source community.
The revolution. But we finally learned how to build perfectly efficient engines, only to realize we are rapidly running out of the high-quality fuel required to run them.
Which forces the entire industry toward synthetic generation and the looming threat of model collapse.
It's an incredible narrative of rapid iteration, and it naturally leads to the next major bottleneck in the pipeline. Because now that developers understand the exact ratio of FLLPs to data required to reach that compute-optimal frontier, the unavoidable question becomes,
How much does all this actually cost in real dollars?
exactly, the economics of optimal training. When you start translating isoflop curves into actual kilowatt hours and GPU procurement costs, you uncover the massive physical infrastructure layer supporting the entire software ecosystem.
The physical reality of the cloud, basically.
We will definitely be diving into those hardware economics in the future. But before we wrap up, I want to leave you, the developer building tools on top of these very models, with a lingering structural question to mull over late into the night.
Oh, this is a good one. Because the implications of the data wall extend far beyond simple engineering bottlenecks.
They strike at the foundation of what these models actually represent. Because if human-written text is a finite resource that we fully exhaust, and future AI models are trained primarily on the simulated thoughts of other machines, does the very definition of human knowledge embedded in our technology fundamentally change?
It's a bit unsettling to think about.
It really is. How will developers ensure their models remain grounded in human reality when the data pool is mostly synthetic?
I think it is the defining architectural and philosophical challenge your generation of engineers will have to navigate.
Absolutely. So keep questioning the underlying architecture. Always check the math on the optimization curves, and never assume a system is efficient just because it's massive. Until next time.